that, I'm not going to show like lots of code, but like lots of good ideas that you can bring home and make use of that. So a couple of words about me. I'm not officially like Go developer or anything like that. I'm officially a data scientist, but I love Go, and I met with Go like in 2010 or something, like in very early versions of Go. And yeah, I basically loved it like from the beginning. Yeah, like everything that I do still related like to data. So even if I use like Go, it's like something nerdy related to things that I want to track something or like make it faster or maybe add some probability on top or like kind of things. I do not actively contribute to open source community, but I'm trying to give it back in terms of like talks. So this is like one of my ways to bring back the community. From another point, I'm also organizer of Munich Gophers, so we have community groups there. So if you used to be like, or if you're planning to go to Munich, just let us know and maybe we're gonna have some Gopher gathering together with you. So speaking of Gophers, there are like many different Gophers like in this room, like in the entire world, and every of them is like super unique, so like focusing on special use cases and thinking about different performance and different tooling. Some of them are like super well known for DevOps. You even today have seen already like many talks how to use like Go and Gophers for I don't know, etcd or like OMP or like many tools. Some of them very well known for web development because you still can concurrently process like many requests, like have like very good connection to database, and we're super happy about that. But what is not very common for Go is using it like for data applications. So it's basically the idea of this talk, and yeah, I'm gonna show some ideas about that from my side of view, like how Go could be useful and what are like good niche for this like small Gophers that look like a scientist. Obviously, it's not like exactly data science. It's like buzzword term. It's more like about data engineering, but we still get there. I'm working like in my working time for Starlight, this like fashion e-commerce platform. So you can really say that you have some fashion companies on FOSDEM. It's like quite strange about that. So we are live like in 15 countries. That means that we have like quite many different requests and different data pipelines that we have like around the places. Yeah, and like the last slide about how many female we have like in our companies, like close to 63%. So don't join us. Yeah, because we need to make it like equally distributed, like guys and boys. And if you here have like most of the boys, there we have like most of the girls. So, so in terms of agenda, it's like more or less like half of it going to be about probabilistic data structures, some explanations, like a simple one, how you can build that, what is theory in the background of that, and afterwards they're going to go through a couple of those stacks that you can basically simplify your life a bit and make use of Go without actually thinking about everything else. Yeah, and the very last point is even more hipster, is like serverless architecture. Architecture is not like real servers. In the background. So a couple of things about types of data that we have and what kind of data is more appropriate for every of those use cases. So if you, one of those like web companies, you must likely have like all those like data sources. So majority of those things are like the biggest volume basically is web tracking. So we have like different metrics, like I don't know, your page load time, or like your behavioral tracking, so you know like what your users do, and after you track some e-commerce things. Some of them are like relatively small and like business intelligence ETLs. So yeah, you still do something like extracting data from one data source and after like put in like somewhere else, go through different extract, transform, and load process. And some companies also have internal services. Let's say in our case it's like huge machine learning process that also need to track different metrics into different things. Yeah, in terms of patterns of access, there are like three main components. Something that you don't care about times that you're gonna process it. Like I don't know, you write like lots of logs, and after you run your Hadoop job, and like everybody's happy, so nobody cares how long it takes actually to process those things. Some of things is like more faster moving. So let's say you have your transactions and you write it somewhere like in a transactional database, and you can wait for, I don't know, like half of a second, or like usually it's like much less. But it's not like super fast, so you don't care if it's going to be delayed like by I don't know, like 100 milliseconds or something. Some of them are like really super fast, and you really need to get your data like as fast as possible, or even do some computations like on stream, basically. So just data coming in, and you already want to have kind of like estimate of things. So you can just like store it into like lots of log files, and after like spin up your Hadoop cluster and like wait for your answer, because it's not really appropriate for that. So in terms of Go and in terms of probabilistic data structures, we're gonna mostly focus like on real-time guides, and even subsetting these real-time guides to something even smaller. So in this case, it's gonna be in-memory real-time. So the things that you will try to keep like in your RAM, and if you wanna get some result, like I don't know, estimate if this URL was already in your cache, you're already gonna get those results like as fast as possible without actually getting like to, I don't know, like getting from file disk, or like getting some strange things that you can do like in the background. Yeah, so first part, probabilistic data structure. So the first question would be like, what are probabilistic data structures? What does it mean? Is it like just giving you some random result and say like, okay, I don't care, like just, yeah, something as a result. So basically, idea, like super rough explanation of that probabilistic data structures, also data structures are trying to use different probability tricks in order to compactly store your data. So you say, okay, like if you really want to store like every of data points, there is no super magical pills that gonna make you super fast, right, and not gonna reduce your memory, because you're always paying like for one resources is like different ones, so you're basically trading those things. And here you use those highlighted probabilistic approaches. I will go like more into details. You will ask like, yeah, when do you need those things? Yeah, like sometimes if you want to do some advanced features and you want to have it like in memory, turns out that even like with terabytes of RAM, it's not always like getting in, and you need to find something like really bigger for this case, and still like keeping like in like accessible and approachable. And we will find that those like initial like terabytes of data could be stored like in like tens of megabytes, and after like even like into kilobytes. It depends like what exactly you need, what kind of function you're gonna have. Obviously, it's not like again magical points that like, okay, here's probabilistic data structures, and you're gonna do like everything like faster and with smaller memory footprint. It's usually approachable for like some narrowed down function, so we'll introduce them. And another point is like all those even buzzwordy things, internet of all these buzzwordy things. The problem of them is that they're like super small. You're not gonna build I don't know, like a small device with 100 gigabytes of RAM, or like any kind of memory, 100 gigabytes or like even gigabytes. So they're like getting like even smaller. But if you're gonna send those like sensors information, you also don't want to send all this traffic like over the internet. So you're trying to find some simple aggregations that you can store like as much as possible data using like this small amount of memory that you have on this device. So you basically will have some kind of like aggregations. Yeah. So first one is Bloom filters. Who is familiar with Bloom filters here? You, everybody. So good. So I don't need to go like way too much into details. Yeah, for those people who don't know what are Bloom filters, idea is we can approximate membership. So you basically can answer the question if we have seen something, or if this request that we are sending is a member of our store set. Yeah, as a default definition from Wikipedia is space-efficient probabilistic data structures, founded like in like 70s by smart guy Howard Bloom. It's actually quite funny then if you find those super efficient data structures, and after you can just like follow the guy on Twitter because he is like still around and still developing like super nice features. Yeah, and the idea is to test whatever your element is your set. So basically, test for membership. Yeah, and as I said, nothing comes just for free. There's like another sentence that finishes basically this definition. It's saying like false positives matches are possible, but false negative are not. It's like what does it even mean, like in this case? And the idea is, the way it works, you can basically ask, I don't know, you, let's say, you build like some antivirus company or something that's gonna check that this particular URL, it could be suspicious because they're sending some viruses through that, and you wanna store like all those URL somewhere that if your browser is basically requesting this URL, you wanna be super fast to know that something's happening there. And this is basically use case. If it's saying that this URL that you're requesting is fine, it's definitely fine because you don't have it. If it's saying that it could be there, it could be false positive in this case. So could be that just like collision and this URL is not super suspicious, but basically majority of those URLs that have like a bad behavior can be covered by those conditions. Yeah, so how it works in terms of implementation and what's actually happening. So basically we have a bit of array, like m bits basically, and we have different hash functions. Those functions, the things that we need to mention about them, that they should have uniform random distribution. So basically, if you run, I don't know, like thousands of different examples or like samples for this function, like all those results should be like across all your space when they should end up. Or how it should work. So basically, we add in like lots of elements. So basically, demo you can find like through this URL. It's also going to be available afterwards. Yeah, and if you add those values, you will see that like every of them has dependent like a number of hash functions, number of bits that you need to check afterwards. For some of cases, let's say we added like 42, 11, 7, 32, 15, and want to check like 10, you see that there's some collisions. So like one of hash functions is like actually checking that something was in this position. But because you have multiple of those hash functions, you always have yeah, like support basically or backup to check like different positions. And it's highly unlikely to basically get into the same positions if your hash function is quite good. And you would ask like, okay, but we still need to kind of guesstimate what kind of size of m we need, what kind of like false positive rate we have, because depending like on application, we wanna, I don't know, have something for I don't know, more sensitive applications like lower one or like a bigger one, depending on memory. Turns out there are some simple estimation for that. So if you want to estimate the first one, like number of hash functions, it's basically quite easy to estimate. So you have like number of basically array lengths, and after you divide by number of elements that you want to kind of have in the background, and after, yeah, it's just like to use a formula. And after for memories, basically for m, there's like another formula for that. It turns out to store 1 millionth of element, this false positive rate just 10%, you need like 600 kilobytes. But if you get it like even smaller, like 1/10%, it's getting like 1.8 megabyte. So basically, if you really think that you have, I don't know, something bigger, I don't know, like 2 bytes per element, and after you need to store like 1 million of them, it's getting quite complicated. Like every time when you need to check, it also depends like on your data storage, how you're gonna check it, because most likely you will not have just like linear space. In terms of Bloom filter, it's quite easy because you just need to compute like those hash functions. Hash functions, you will say that it's quite usually difficult to compute because most of hash functions are from cryptography and stuff like that. But in this case, we didn't use those type of functions. They're simpler. And there was like another research that you can do not compute like, let's say we have a number of k is 5. You don't need to compute like 5 of them. You just can basically offset them. So you will compute like one hash function and have offsetting for different of them. Yeah, so as you have seen, number of memory footprint is like quite small, but we will see that in future it could be like even smaller. Yeah, so what are use cases? Use cases are caches. When you want to know that element is like somewhere and we don't want to check it from the cache like as fast as possible and without like I don't know, like accessing something like that much slower. I know if it's a hard disk or some network request or something else. It's actually used in databases. HBase and Cassandra is actually usually deployed actively. It's also used like for Chrome. If you go to URL, it's going to check if this URL is basically in a list of suspicious URLs or something could be wrong there. And it's very easy to distribute like for this use case. There are a couple of examples when you can find this implemented. Those are like pure Go implementations. Those are like slightly extended. I will mention it like a bit later. And this is like super easy and cheap solution for you. So basically, guys from HashiCorp, they developed a project that basically Bloom daemon or something. That the guy is gonna do like all magic in the background, and he just like sends this request. So if you don't want to spend your time in order to implement Bloom filters because you're not exactly sure how much benefits you will get, you can just start with this daemon and see what kind of performance you will get, and yeah, just play it around and see the kind of results. And this is basically a Go client that you can easily use for that. Yeah, and if this kind of filter is quite simple, you can always make it like more complicated. So one of them is cardinality estimate. So you can kind of like estimate how many unique elements you have seen. So idea is like super simple, even simpler than Bloom filter. Every time when you edit something beforehand, you will check if this element is already there. So if this element is existing. And if it's not existing, you basically have a counter on the side who's gonna say like just +1. And yeah, basically like that. Another problem that you not always want to have the size of M like just static, because you don't know like how many requests you're going to receive like afterwards. So there is a way to basically have like a different layers, and basically the way to scale those Bloom filters. And the idea of that so let's say you have initial setup of 4 functions, and like M is I don't know, like some number basically. And after you see that I know your traffic is like much bigger, or like your hash functions are getting exhausted for this case, you can basically add another layer of another hash function. And basically this one is checking not k function initial one, but k +1. And if even all of those k initial functions are already having like lots of like ones, like yeah, bits that are already set, the k +1 function is already empty. So basically every time when you check it, it will provide information that this element is like quite new. Yeah, and another nice thing about Bloom filters, you can also merge them. So if you have like a smaller ones, you can always bitwise merge them together and see the result. Yeah, there is also another idea of counting Bloom filters. Like every time when you will add these values, you not only just set it to 1, but increment it by 1. And after you can see what's the smallest value there. And it's basically a very similar idea of count min. It's frequency estimator. In this case, we have not one-dimensional space, but like two-dimensional space with columns and rows. And the hash function basically associated with every of those rows. And then you add like a value, you're gonna add a value basically to, or yeah, if you see the element that you wanna count it, you're basically gonna increment like every of them. And as it sounds from definition, the idea is that afterwards when you're gonna check what are the values there, you can basically check what is the minimal value. It's basically where count min is coming from. Yeah, so now we come into something more complicated with repeating parts like log-log, or sometimes hyperlog-log plus plus, the new one from Google. And the idea is it's cardinality estimator. So you basically want to know how many distinct elements you have seen, and yeah, like have some functionality with that. And as you have seen already with hyperlog-log, that was quite memory efficient, but in this case, it's even cooler, maybe because of this log-log part that we'll get there. And the idea is that you can estimate cardinalities of 10 power of 9 with typical error just like of 2%. And for that you need just 1.5 kilobyte of memory. You would say like, it's something strange, it's not like really going to be happening like that, because like so small amount of memory, and you can get like such huge numbers. Think about IoT would be like a good example here. So idea here is, initially it's like quite difficult to get into that, but I will try to explain it as simple as possible. So before we had like already those hash functions, and hash function gonna provide you some I don't know, number basically that's gonna define your position where you're gonna put this value in. But now things that hash function gonna provide us stream of bits. So it's basically binary representation of these numbers that we're gonna get afterwards. And again, those hash functions uniformly distributed. And the idea is that every of bits is basically totally independent from one from another. So if you know that here is 1, it doesn't give you like any information of the kind of next bit, so like totally independent. Yeah, so probability 101 or 10. Basically, idea, if you have, what is the probability that first bit is 0? It's like 1 of 2, right? Because there are only 1 or 0. The second bit is the same, right? What is the probability that you have like 5 consecutive zeros? It's basically power of 5. And if you have like n of them, it's basically the same story, but with power of n. You're like, okay, this sounds simple, but how it's actually related to that? Yeah, we will get there. So let's say if you have n32, like quite big one, right? Odds of that is 1 divided by 2 in power of 32, basically. So expected number of samples that you kind of like store into that is quite big. But what do you mean by storing? So we have like super rough assumption. We say like, if we see, if you see some element like that, we will say that the probability of that is like super low, right? Because like the probability to see this element is quite low. But the problem here is that this element could be just random. So like the first one that we will get there will be I don't know, this kind of number, and after it's going to screw all of our counters. Yeah, and in order to say that we have seen a number of these 32 zeros, we just need to store like 6 bits for that. This is basically where the name coming from. So the first block is going to be like saving this number like in binary format, and after storing those number of zeros that you can see again like in a binary format. Yeah, so you would say that, okay, if we see the number that has, you know, like 5 zeros, is it like actually because probability is that low, or because the number happened to be super low? And this idea is that we have like a multiple registers. So multiple of functions that we have there could give like a different results, and even like the first one have seen like 5 zeros, different one will provide like a different value. So we will basically avoid those false numbers that are going to screw all our counters. And in order to store like multiple of those registers, or basically result of so like registers coming from those values that you store in there, like how many zeros you have seen. And in order to store them, we're going to say that like first number of bits are going to be register index, so basically it's a way to say what index we can access, and rest is going to be stored for actual like values. So like in this case, like the stream that we receive here, first two is going to be register index, and second one is going to be like actual value afterwards. In order to get like multiple of those registers, you can just like shift it over and see what kind of value you're going to get there. Yeah, there's like some simplified version of code. I mean, it's not super simplified, it's like really from one of the suppositories that they're going to link like afterwards. But the idea is that you get like this item that will get like all of your bits. After you can shift it to have some number for index and some for like real value. And after you can compute number of 0 bits. And based on this like 0 bits, if it's like bigger than it was before, we basically update these values in your registers. The only problem, because here we basically checking what is the bigger value, it's going to be quite difficult to merge across all those registers and see what's the actual value. Because let's say we have, I don't know, like 5 different values, and one is showing like 4 billions, and one is showing like 25. Like what kind of value you're going to get there? Idea there that, what kind of aggregation function you will use? Like mean, max, average, median, or something like that. The problem there is that we have like lots of those like outliers that basically just screw like entire aggregation function, and there are like some ways to do it more appropriately if you want. So originally they were coming from geometric mean. So basically idea would be that you multiply all of those estimators from every of those registers, and after you have a root square of k basically. So if you have like 5 elements or 5 registers that store those values, you will multiply like all 5 of them, and after you will get like a root square, not root but a square of order 1 and 5. So it will help you to avoid just like outliers, but not that much. Another idea would be to use harmonic mean. This one looks even more complicated, but in order to compute it, it's not that hard basically. So you divide like 1 by register value and like sum them all, and after you n divided by like all the sum. And basically it's more or less all in terms of implementation. So there's also some magical aids that's coming from some researchers, and ideas that you still will get like slightly biased. And this A was pre-computed by a test set, like initially it was coming from Google, I think, but currently you can just like reuse it. It's like defined in this original paper from this one. Here's also an example of how you can compute it. Maybe I can just show it. Oops. Yeah, that was like the first one with like all these values that you're adding into the tool filter. And there's like a second one that you can basically do step, and you see register index. Yeah, unfortunately in this demo we can see values that is generated, but the idea is that this one is like stream that you receive from there. This one is like index, this one is actually value that you store in your registers. And if you run it like for a long time, you will see that for smaller one it's getting like quite small, but at the end of the day it's getting like quite close to 0. And here you can see how it's changing. Yeah, and there's also like values that you store to registers. Yeah, so where this one is used? More or less like everywhere. So basically all of those like databases that you're gonna say, I need to estimate cardinality and see like how many distinct elements we have. It's used in Redis, Postgres, Redshift, and all kind of guys. Even like in Spark, it's used for some use cases. So if you wanna play around with that, there is again good demo, unfortunately written like in C, but you still can like access it through a special API, basically similar to one that you mentioned before. It's again written by guys from HashiCorp, but it's quite easy to get it and see what kind of performance you will get like with the results. And this one is one implementation by Google. I think not original Google implementation, but the guy who implemented it was actually for Google. So Google implementation. With this part, you already have seen what kind of benefits you will get in order to store in small memory footprint, like all those values. But sometimes, like just storing values and getting like those simple aggregations, like I don't know, like how many events you have seen, or is it like this event is member of something, is not enough for all this like data blocks. That's why like second part is going to be, or like second smaller part going to be about pipelining. In this case, pipelining is just basically data process of connecting from A to B. And here I will go through some open source and cloud providers that can help us there. So first of all, like open source, there's like very common like Lambda architecture, and like that one of layers is like fast ones that you can store all kinds of things or like get results quite fast. And one is like bytes if you don't care about performance. But basically like all the results that came like afterwards. In terms of open source, I will make it like a bit faster because those are like quite common products. Apache Kafka is like a good guide to start storing those values. Obviously, you will not get all those fast estimators from there, but you can get all values at the end of the day. Idea is that you have like many different brokers in your clusters. Every brokers could be like partition like inside. And when you write it in, it's basically append only log files that will get like all this stuff inside. So it's quite simple, that's why it's quite fast to scale. Those are like a bit details how it's basically implemented. You have some network layers that will receive all of those threads, and after go through the channel to basically API layer, and after it's going to be stored to management, appending things basically. This is also replication, but it's not related to like part of the talk, but it's quite scalable. In terms of Go, if you want to use Go in order to write to this like Kafka stream, there is like a good library from Shopify guys. It's supporting like last versions of Kafka, so it quite easily can implement these ideas. And there's like another client that is not that popular. And this is like really simple to use. You basically define like different, so in terms of Kafka and afterwards Kinesis and PubSub, they have consumers and producers. Producers gonna produce like all the information, write it somewhere, and consumer gonna get it from there based on this like timestamps that you have. So you just create like localhost Kafka consumer, and after you write some values and next one. You have some message that you want to add there, you have like a topic, and like values that you're going to string encode inside. Like nothing really complicated. But the point is that with all this like open source stack, you can get it like slightly to the next step. It's not like only about writing values and having some simple aggregations, but getting something more advanced. So this idea is how you can do processing like this Spark or like Hadoop, like depends like on your use case. So basically Kafka here is like to write in those logs after you have some aggregations through your Produce cluster or like Spark cluster or whatever you use there, and you will get results afterwards. And basically for MapReduce there is also Go library, Dr. Mr. Go or whatever you call it properly. This one is helping you to write all these like MapReduce jobs in your favorite language, so Go in this case. As a result, we can cover not only like first entry point of writing data in, but also like processing all those things. It's quite flexible because like all of elements you need to be installed like on your own and maintained on their own. But maintain is like quite expensive, so it's not that easy to set up or just like start playing. And the idea of this like data pipelines that it's getting kind of like low level because you give you attention to irrelevant details like how to scale it, how to maintain it, and stuff like that. So idea would be that we can make it somehow automatically scalable for you. One of them is I will go like through two platforms. One is Amazon, one is Google, one is Kinesis basically. And the idea of Kinesis is kind of like hosted Kafka if you want, but Amazon does everything for you and gets your money for that. It has like different partitions. It's like automatically distributed your different topics or streams through different ones, and after you can get results with the same Go consumer, for instance, and you can decide what you do like afterwards. There is also Amazon SDK for that. It's quite okay, I think, like nothing like really bad is happening there. It's easy to use afterwards. So if you want to put some records, you define your Kinesis session, you define your entries that has like some payload after your partition key, and that's all more or less. In order to retrieve from there, it's also not that complicated. So you can use Go as a fast and scalable language in terms of many coroutines in order to process data from your streams that basically scalable for you by some vendor providers. So you don't need to spend the most expensive time in order to get like something in the middle that you don't want to maintain. And there are some additions that can basically make it even easier, so you care only about writing inside, and this idea of Amazon Firehouse is basically automatically delivering to some of your data sources, so for instance like S3 or Redshift or whatever you decide there. So now you care only about entry point, and you basically decide what kind of priorities you want to have. Like if you want to put like all the data, you just like write to Kinesis. If not, you just I don't know, use some Bloom filters or approximators there. Yeah, and you can run some analytics basically on the same data sources. Yeah, this is like one of like real-world pipelines. So we have some product processing department who does like lots of machine learning stuff, and because it's like totally different departments, they don't have like any connections to us. The only way that we communicate is like data pipeline. In this case, it's like Amazon Kinesis that they write events in, and after we get them from there. So it's quite convenient in order to have cross departments communications that you don't need to think that, okay, we store it somewhere and after we change it to implementation, so like all the APIs are changed. Yeah, you would say like Amazon, what about Google? Yes, there are some Google guys around. So idea of that is like pretty like similar to the same conception from Amazon. You have like PubSub in order to write your events. You have data flows kind of hosted, I don't know, like MapReduce or like Spark or whatever, like more convenient for you. And also you have BigQuery as already kind of like representation of structured data. In terms of that, PubSub is also has like topics, and in this case they call subscriptions, and yeah, and you basically can write your topics inside, and Google will scale this pipe for you automatically, so you don't need to focus on the things that you don't want to. There's a library for that, hosted by Google Cloud Platform team on the GitHub, and yeah, it's quite flexible. So what you can do with this data afterwards, there's Google data flow, and the idea is that you can define like kind of like they call it also pipeline, but also slightly different. So you want to know what kind of aggregations and what kind of function you want to apply. So for instance, you have some inputs where data is coming from. In this case, it's like PubSub, for instance, or BigQuery, or like many of them. After you can do some transformation, you can do some window functions and stuff like that. And basically, it's quite flexible to use those things. Unfortunately, right now they support only Java and Python, but there was some rumors about Golang that is going to be some future plans. Nothing yet released, but hopefully you will be able to write your Go stuff for this part as well. Yeah, and just architecture is like very similar. You have some job manager, and it will get and deploy to all those compute nodes, and yeah, it's like automatically scalable and proximate to your size of data. And there's some device. Yeah, like as a benefits here, you don't need to care about maintainability of those things, so you can basically focus on things that you want to have like as a core business of this stuff. You don't need to split up like batch processing and stream processing. Basically, the same model going to be defined for data that moving fast and data is going to be processed like over the night. And fortunately for folks that already use either like Spark or Flink or stuff like that, you already have support for those things in order to run like data flow on those platforms. So you can basically play around on your local machine and after get it something bigger. Yeah. Or if you will decide to use data flow, you can basically switch back to Spark or Flink. Yeah, there's like kind of like new concept of that sometimes you can have those events processed like even without actually having servers, means like not having cloud, but something like totally different. Not totally, but slightly different. So from Amazon they call it like Lambda. Yeah, hip Jewish way to call product, but whatever they decided there. And the idea is that you have like many of the services already in your platform. It could be something simple as Amazon Kinesis, or every time when you write to file disk, like simple storage, stuff like that, you will get event from there. And before you're gonna, like back in days, you're gonna pull this data from there and do some processing, so that means that you need to know how many of them you need, like how often to pull the stuff. But there's like another way. So you can basically say like every time when event is coming, I want to run some functions on top of it. So in this case, you don't need to pull anymore, just like push it to you, and your resources basically executed like on demand. There's like more simplified version of that, so you have like Kinesis stream, and every time when something is coming in, you basically will execute some function. This product was introduced like, I think 2 years, but like for the last 2 years we never tried it like properly. The problem was that you cannot really deploy all those things. So you can create function like in UI, you can do some like crazy stuff, but it's not really maintainable, so you don't have like proper deployment strategy. And recently we started to work on this like Apex project, and the idea is this like Go project to basically maintain all of those Lambda functions. And the idea is that you can define your code in like Golang like as well, but there are also support of I think like Python, Node.js, and JavaScript. And this guy is going to help you to maintain all of your functions. So it will create all of your builds, like do all the magic like in the background, and for you it's quite convenient. So as a result, you don't need to care even about those like cloud foundations that will help you to process those data. You just like have I don't know, like input streams that triggers like every time when you write some data to to your database or when you upload the file and stuff like that. And these functions that are going to be executed is quite independent. In order to use like some simple Go example here, you just like have a function that goes to main handler, and after you will receive like a JSON, for this case from, I don't know, like for instance we use like notification to Slack. So like every time when something is happening wrong, you're going to send a notification to, like from CloudWatch logs, we will have information about logs, and after send notification to Slack that something's happening. So you don't need to care about any kind of infrastructure like in the background. You just like have your functions that are already like automatically deployable there. Yeah, in terms of that, you have like possibilities that all of your functions that defined like for Lambda, they store like under the version control. Before it was quite difficult to do it properly. You have like all integration tests, so you know that if something is coming in, you can have like Jenkins jobs who will check your pushes to master, let's say, and after like deploy all your functions automatically, and you still can use Go for that. Yeah. So speaking again, or having some short like follow-up for that, Go could be quite useful for all of your high-performance data pipelining. So you can do quite easily, not super easily, but easily, all those estimators that I mentioned today. Unfortunately, right now, library of Go is not that big as library of Python. So, for instance, you cannot do like pure data science in Go. There are some projects that actually trying to fill in this niche, but it's like community is basically moving to slightly different direction. And from another point, maybe it's even okay-ish. I mean, it's not that big problem for me as a data scientist because, for instance, I can use like R with even like bigger standard library, and if I want to implement some service that's going to do some, I don't know, let's say A/B testing or stuff like that, I can always switch to Go and make it concurrent and fast and high performance. Yeah, so use the tools that you wanna use there, and then think about language like as a primary decision maker for you. Yeah, thank you for your attention. There's also a list of related talks and links and stuff like that, so just go to them and when you